So the question is how do we go from essentially a sea of magma to a nicely differentiated Earth? Now you can see when it comes to differentiating the Earth, we can do it in one of a couple of ways. We can do it based on compositional characteristics or mechanical characteristics. So the mechanical characteristics are quite straightforward. Is the layer solid or is the layer liquid? In terms of compositional characteristics, the question is, what is the layer made of? So, these layers are all chemically distinct from one another. Now, these two types of differentiation will obviously not align, as you can quite clearly see. The inner core and outer core are separate based on their mechanical properties, but they have the same chemical composition, so they are combined when you consider them as part of a compositional system. So, just bear that in mind. I should also point out, by the way, that this diagram here is going to come up a few times, and it's also a diagram that does make a reasonable amount, reasonable number of appearances in midterms and occasionally in the final as well. So really make sure you know this diagram here and make sure you know each of these individual layers. Just going to give you that heads up now. Okay, so geologists separate the internal layers of the Earth as they're using mechanical or compositional properties. So first of all, let's start thinking about the mechanical layering. As I said, the mechanical layering simply goes, is the layer solid or is the layer liquid? So let's think of the lithosphere and the asthenosphere. They're considered different layers. So data indicates that both the continental and oceanic crust are not detached from the mantle. They are in fact actually attached to a thin layer of solid mantle rocks that are stuck onto the bottom of them. So from a purely mechanical point of view, we have a solid continental crust, a solid oceanic crust, and a solid layer of mantle rock stuck onto the bottom of both of them. So what we've decided to do is we've taken that package and we've combined it all together, and we've simply called it the lithosphere. It doesn't matter that they all have different compositions, the continental crust and oceanic crust and those mantle rocks, all completely different. But from a point of view of their mechanical properties, they're all solid. So geologists lump them all together and call them the lithosphere. I should also point out, by the way, that this contact between the continental and oceanic crust and this thin layer of solid mantle rock stuck to the bottom of them is of course called the moho. It's a term you've probably come across before. Now, underneath the lithosphere we have the asthenosphere. So the asthenosphere is made up of iron magnesium silicates. And the transition from the lithosphere to the asthenosphere is obviously defined by a change in mechanical properties. So the lithosphere, so the asthenosphere, I do apologise, is mechanically weak. So it will flow, it will undergo ductile deformation. So modelling suggests that the asthenosphere is a mixture of solid material and a small volume of melt, also referred to as magma. So you need to think of it something like a slushy. So a slushy is mostly ice, but in between the ice crystals you obviously have your syrup of choice. So this melt appears to be constrained to the upper, concentrated should I say, to the upper 100 kilometers of the asthenosphere. So the asthenosphere is approximately 700 kilometers thick. It looks like the upper 100 kilometers of it is quite magma rich and quite solid poor, whereas the lower 600 kilometers is more solid rich and more magma poor. Now this is important because it means, because the upper layer of the asthenosphere is more liquid, it gives essentially a layer on which the lithosphere can float and move. And of course, if you think about it, that's obviously extremely important when it comes to plate tectonics. So the combination of the little bit of mantle rock stuck onto the bottom of the lithosphere and the asthenosphere is also sometimes referred to as the upper mantle. So I've just thrown a whole load of terms at you. So let's just try it one more time. The oceanic crust and continental crust, they are chemically different, but they are both solid. And attached to the bottom of both of them, we have a small piece of mantle rock. And so a small layer of mantle rock, should I say. So the oceanic crust, the continental crust, and that small bit of mantle rock are lumped together as a lithosphere. Underneath the lithosphere, there is a semi-liquid layer on which the lithosphere floats, and that is the asthenosphere. Now, because the asthenosphere and that little bit of mantle rock stuck onto the bottom of the oceanic and continental crust have the same composition, it means they are sometimes referred to as a unit, and that unit is sometimes referred to as the upper mantle. So I hope that made things clear. So the asthenosphere's lower boundary is about 700 kilometers down, and below the asthenosphere we have the mesosphere, also referred to as the lower mantle. Now the mesosphere is solid, and it's made up of magnesium iron silicates. So as we move our way through the mesosphere, we eventually end up in the outer core and the inner core. Now the outer core and inner core aren't made of silicates. They're made of, it's an iron nickel alloy, so it's going to have different properties in terms of melting. So the outer portion of the core is liquid and the inner portion is solid. So from a mechanical point of view, they are considered distinct, and so they are classified as the outer core and the inner core. In terms of compositional layering, it's purely based on the chemistry. Doesn't matter what the physical properties of the layer are, we're exclusively interested in what they're made of. So the core consists of any material, or should I say contains any material which is dominated by iron nickel alloy. So that's obviously going to include the inner core and the outer core. In terms of the mantle, well, the mantle contains any material which is dominated by iron magnesium silicates. So that's going to include the mesosphere, the asthenosphere, and that thin little bit of mantle rock stuck to the bottom of the continental and oceanic crust. In terms of the continental crust, well, that's dominated by sodium, potassium, calcium, aluminum silicates, whilst the oceanic crust is dominated by calcium iron silicates. So you can see that each of the four units has a very, very distinct chemistry, and based on what your rock is made of, it will fall into one of those four groupings. Should I say what your layer is made of, it will fall into one of those four groupings. Okay, so what is actually the driving force behind plate tectonics? So when it really comes down to it, plate tectonics is driven by mantle convection. So what we have is the same kind of situation that we get occurring in a pan of boiling water. So down here at the base, the mantle gets hot. Because it's hot, it naturally becomes buoyant, and so it rises. As it rises, it steadily gets cooler. As it gets cooler, it begins to become less buoyant, and so because it loses buoyancy, it starts to sink, and so we get these convection cels forming in the mantle, where hot mantle rises and cold mantle sinks. So straight away we have these convection cells moving, and those convection cells are naturally going to pull the crust along with them. So this piece of crust here is going to be moving along with the convection cell. The other thing is that when you have two convection cells running along with each other, so we've got this convection cell is coming up here and going this way, this convection cell is coming up here and going this way. Well, that means this piece of crust over here is going to want to go off to the left, whereas this piece of crust over here is going to want to go off to the right. This means this bit of crust right here in the middle is going to be being stretched in both directions, isn't it? And of course, as you know, crust is solid, so it doesn't stretch, it breaks. And so these are the locations in which we're going to form the divergent plate boundaries, because the crust is naturally being stressed by one convection cell going this way and one convection cell going this way. Okay. In the case of subduction zones seem to be associated with areas where the mantle is actively going downwards. And this isn't a huge shock. So what we have here is new crust is being made at the spreading ridge. The crust is moving laterally away from the ridge. It's hitting the continental crust, and the mantle is descending here, and so it helps to pull the crust down with it, the oceanic crust down into the mantle as it goes. So mantle convection appears to be one of the contributing factors to plate tectonics. Now the next question is well, why is the mantle convecting? And the mantle is convecting quite simply because it's hot. There's lots and lots of heat in the Earth's interior, and that heat comes from two sources. The first one is the obvious one, radioactive decay. So the Earth's mantle is absolutely stuffed with radioactive isotopes, so things like potassium-40, thorium-232, uranium-235 and uranium-238. And these isotopes are constantly breaking down, they're decaying radioactively, and of course as part of that process they release huge amounts of heat. The other contributing factor to the Earth's internal heat is what's called the heat of accretion. So if you remember, all the way back in the first lecture, we were talking about how the planet Earth formed from lots of bits of rock accreting together, so sticking together. Well, when those pieces of rock stuck together, they didn't just stick together gently, they would smash into each other, they would hit each other head on, and they would merge to form a new piece of rock. So this process of pieces of rock hitting each other, that's not a gentle process. It's a powerful, energetic event. And some of that energy, when the impact occurs, will be turned into heat energy. So think about it. If you have hundreds of, if you have billions or trillions of these impacts that go to form the Earth, well, each one of those impacts is going to contribute a small amount of heat energy into the Earth. And so when you do that times 1 trillion, well, that's going to be a lot of heat, isn't it? So we also have this thing we call the heat of accretion, and that's the residual heat from all the impacts that went to form the Earth. So from these two sources, that helps to explain, why the Earth's interior is hot. And obviously once we know it's hot, well, we then know that hot mantle will rise and cold mantle will sink, and so we get these convection cells. So the next question is well, if the mantle keeps producing heat, it's going to keep getting hotter and hotter and hotter, isn't it? And eventually, if the mantle got too hot, bad things would happen. And actually, in the last 2 slides of this presentation, I'll show you an example of what bad things can happen if the mantle gets too hot. So in order to stop the interior of the Earth overheating, the Earth obviously has to lose heat. So the question is how does it lose heat? Well, it loses heat in 4 ways. The first way is it loses heat at spreading ridges. So underneath these divergent plate boundaries, we have mantle rocks melting to produce magma. And so that magma rises through the crust, cools down and solidifies to form new oceanic crust. So what's happening is you're taking heat from inside the Earth, using it to melt rock, and then transferring that heat to the surface where it's lost to the oceans and the atmosphere. And so that's one way of getting rid of heat. The other way we can get rid of some heat is by subducting cold oceanic crust. So this oceanic crust here, subducting down into the mantle, is going to be, comparatively speaking, quite chilly. And so it's just going to be like dropping an ice cube into your cup of coffee. It's going to help to bring down the temperature a little bit. Obviously, the simplest way of losing heat is through conduction. So heat will simply conduct through the crust and then be lost to the atmosphere or the oceans. Most of the heat is conducted through the oceanic crust because it's the thinnest. Remember, continental crust can be up to 70 kilometers thick, so it doesn't conduct heat, hugely effectively. Oceanic crust is only about 5 to 8 kilometers thick, so heat can, so the heat can transfer through it relatively fast. And the final way are mantle plumes. So a mantle plume forms right down here at the core mantle boundary. So we have an area of mantle that gets superheated, it's stupidly hot, and so the mantle melts, and the resulting magma comes flying up through the mantle, and it gets stuck at the base of the crust. And we see mantle plumes because we know mantle plumes exist because they create these linear island chains like the Hawaiian island chain. So that's also another way of taking heat from deep in the mantle, transferring it up, and obviously getting rid of that heat in the form of magma, which gets pushed out onto the Earth's surface. So these are the methods by which the Earth's interior helps to maintain balance. So the final thing we're going to discuss is we've spoken about how the Earth's interior is very, very hot and it loses that heat, and losing the heat is a good thing. So the next question is well, what would happen if the Earth's interior couldn't lose that heat? Well, we obviously can't see any evidence for that on Earth, but we can go to other planets, and the planet we're going to look at is Venus. So the thing you'll notice about Venus, if you look at the surface of it, is Venus is actually quite smooth. Compare that to other things, other planets and satellites that you're used to seeing. Think of the moon. It's covered in impact craters. This is Mars, covered in impact craters. Now this area here is not covered in impact craters because it used to be an ocean and the impact craters have been filled in. But these areas here that haven't been covered by ocean sediments, you can see covered in impact craters. This is an asteroid, one of the larger asteroids in the asteroid belt called Vesta, and once again you can see all of these impact craters. So we know that all the other planets in the solar system and satellites and asteroids are covered in impact craters. Now we know that Earth isn't, because Earth is an active system. The crust is constantly being recycled. But what about Venus? Well, Venus doesn't really have plate tectonics. It does have some plate tectonics, but not in the same way that Earth has plate tectonics. So Earth's plate tectonics are lubricated by water. Water helps plate tectonics to happen. In the case of Venus, there's no liquid water. So that means plate tectonics is a very difficult thing to occur for Venus. Can't do it easily. And so when we look at the surface of Venus, we notice that it's got very few impact craters. Now, if we date the surface of Venus by looking at the number of impact craters, we see that the surface of Venus is only about 500 million years old. That is young, geologically speaking. So the question is, well, what happened to all the crust that was older than 500 million years? So clearly, something quite dramatic has happened. So the question is, what? And the process that we believe occurred is something called catastrophic resurfacing. So catastrophic resurfacing is simply the mantle got so hot that it actually caused the crust to melt. So it melted all or a significant portion of the crust of Venus. And so about 500 million years ago, Venus's mantle reached a temperature where it started to melt the crust. And so the crust melted. That obviously destroyed all the old crust, so we lost all the impact craters. And eventually, once the mantle had cooled down enough, a new crust formed, and that's the crust we see now. And so Venus is a wonderful example of what could happen if the Earth didn't have the capacity to lose that internal heat. So we know there are two types of crust. There's oceanic crust and continental crust. So obviously the oceanic crust makes up the majority of the seafloor. The continental crust, shock horror, makes up the majority of land masses, and of course it also underlies the shallow seas along the coast, which the portion which we refer to as the continental shelf. So oceanic crust, seafloor, continental crust, the land masses, and the continental shelf. So oceanic crust is actually relatively thin. It's only about 5 to 8 kilometers in thickness. In contrast, continental crust can be anywhere between about 10 and 70 kilometers in thickness. So there's quite a big difference there. Now, this is obviously going to cause a difference in height, because if you think about it, so think of the oceanic crust as a block of wood, and you put it in water. Well, that block of wood, let's say it's an 8-kilometer thick block of wood, and it's sitting in the water. Well, in order for that block of wood to be stable, 4 kilometers of the wood need to be underwater, and 4 kilometers of the wood would be above the water level. Yeah, in that way the piece of wood would be stable. So that would mean that 4 kilometers of the wood would be above sea level. Now, think of the continental crust. Let's say it's 70 kilometers thick. Well, that would mean same situation. You've got a 70 kilometer thick piece of wood, put it in water. 35 kilometers of that would be below sea level, and the other 35 kilometers would be above the water level. So the continental crust, because it's thick, is naturally going to sit higher than the oceanic crust. So that's why the continents naturally form highs and the oceanic crust naturally form lows. And so the oceanic crust, because it forms the low, well, that's obviously the area that's going to fill in with water, because we are lucky on planet Earth, we have loads of water moving around, and so that water is going to naturally congregate into topographic lows, of which the largest topographic lows are the ocean basins. Another reason the oceanic crust sits lower than the continental crust is also because of its density. So oceanic crust compared to continental crust is actually quite dense. It's heavy. Continental crust, on the other hand, when compared to oceanic crust, is lighter. And so once again, because the continental crust is lighter, it's naturally going to float a little bit more easily on the asthenosphere. And so it's going to sit that little bit higher than the oceanic crust. Once again, that's going to contribute to this difference in topography. The continental crust is going to stand high. The oceanic crust is, comparatively speaking, going to be a lot lower. And then finally, there's the material that the crust is made from. So oceanic crust is made from a mixture of basalt, gabbro, and peridotite. So the basalt essentially represents the top of the oceanic crust. That's the area that would be, the sea floor itself, the bit you could actually walk on. The gabbro represents the magma chambers underneath the solid crust. That's actually, which has the magma to actually feed the creation of new crust. And the peridotype represents the material that's melting to form the magma, which goes into the magma chambers, and the magma chambers eventually cool down to form the gabbro. Don't panic, I'm going to show you a picture in a few slides' time that's going to make that a lot clearer. In terms of continental crust, well, continental crust consists mostly of granite, gneiss, so remember gneiss is a metamorphic rock. Compositionally speaking, it consists mostly of quartz and feldspar and a few ferromagnesian minerals. So, in terms of what it's made from, it's actually very close to granite, so they're very similar rocks. And granodiorite. Granodiorite is an intermediate igneous rock, so it's not quite as rich in potassium feldspar and sodium plagioclase feldspar, but it's slightly richer in things like calcium plagioclase feldspar and has a little bit more of the ferromagnesian minerals, but it's not, but it's still a very feldspar dominated rock. So the continental crust is made from intermediate and felsic igneous rocks and very feldspar rich metamorphic rocks, whereas in comparison the oceanic crust is made from mafic and ultramafic rocks, and that obviously explains the density. Mafic and ultramafic rocks tend to be heavier than the more felsic and intermediate igneous rocks. So when the plates are separated by three types of plate boundary. So there are the plate boundaries where the plates are moving apart from one another. Those are referred to as divergent plate boundaries. There are the plate boundaries where plates are coming together and crashing into each other. Those are the convergent plate boundaries. And there are the plate boundaries where the plates are simply moving past each other. Those are the transform plate boundaries. And you can see that for divergent and convergent plate boundaries, there are subgroups. Okay, so this diagram here summarizes the boundary types, the risks, so volcanoes, earthquakes, tsunamis, whether oceanic crust is made or destroyed, and any other associated features. Please take some time and make sure you write this down, because this table does have a habit of occurring in tests sometimes, or questions based off this table can appear in tests. Okay, so now let's think about our different types of plate boundaries. So we're going to start off with constructive plate margins, also called divergent plate boundaries. So divergent plate boundaries come in 4 stages: stage 1, stage 2, stage 3, and stage 4. So stage 1 typically is focused on a piece of continental crust. So you'll have your piece of continental crust, and your continental crust will be sitting above 2 different convection cels. So remember, the mantle is rising up, convecting and coming down. So it's convecting one way, and on the other side it's convecting the other way. And so because this area of mantle here is going to the left, and this area of mantle here is going to the right, it starts to stretch this piece of crust in the middle. So this area here is under what's called extension. It's being pulled. So the rocks are being stretched. And once again, as we know, rocks behave in a brittle fashion, so when they start getting stretched, they don't get drawn out like a piece of silly putty, they break. The other thing is that because we have these 2 convection cels, I'm just going to go back to the previous picture here. So we have a situation like this. So we have one convection cell coming up here and one convection cell coming up here. Now, if there is something like a mantle plume forming, it's naturally going to be channeled up here between these 2 convection cells. And so this means that you'll also get large amounts of magma gathering underneath this divergent plate boundary. So we not only have the convection cell pulling this piece of crust this way, and this piece of crust this way, we also have magma naturally pooling at the point where these 2 convection cells meet, and so this magma is obviously hot, it's buoyant, it wants to rise, and so it starts to cause the crust to dome. This stretches the crust even more, and so this area of the crust here is being stretched, it's being heated, and of course it begins to fail. Not really a huge shock there. And so obviously when it begins to fail, it begins to crack. Of course, we know by now these cracks are referred to as faults. So we have blocks of rock moving past each other, and these faults make the perfect pipework through which the magma can move to the surface. So what happens then as we move on to stage 2? Now this is the point where we form something which is referred to as a rift valley. So what's happened is this piece of crust over here is trying to move to the right. This piece of crust here is trying to move to the left, and obviously, as we know, this area in the middle is being stretched, it's being extended. So we know the crust will fail in a brittle fashion, it will break, and that means the crust will split up into these chunks of rock. And these chunks of rock will essentially move relative to each other, and because this piece of crust is moving this way, This piece of crust is moving that way. The rock that's in the middle here drops down to fill the gap. And so we end up forming this topographic low, this valley. Okay. Now, obviously, as we also know, the valley is going to fill with volcanoes because we have all this magma down here. And some of that magma is going to make its way along these fault plains to the surface, and it's going to be erupted onto the surface. And then the final stage is eventually this piece of crust here is going to get very, very thin. So if we go back to the rock presentation when we're talking about igneous rocks, you'll remember there's a form of a form of melting called decompressional melting. And that's when we take a piece of rock which is very, very hot but under very high pressure, and we suddenly decrease the pressure. And if you remember, when we decrease the pressure quickly, that hot piece of rock will suddenly melt. And so what we have here is we have an area of rock directly below this rift valley that's all of a sudden finding itself under much lower pressure. Because remember, this piece of continental crust here can be anywhere between about 10 and 70 kilometers thick. This bit of continental crust here, because it's, being stretched out, it's now, it's much, much thinner. And so that means the mantle rocks underneath the rift valley are under much lower pressure, but they are still very, very hot. And so the mantle under here will start to melt. And so what we'll see is we'll see the magma here beginning to melt. So the peridotites will begin to melt, and that will start forming mafic magma. If you remember, mafic magma is what goes to form rocks like basalt and gabbro. So eventually we reach the point where the crust has been stretched so far that the mantle really begins to melt. At this point, this mafic magma is going to start making its way to the surface. It's going to start cooling, and now we have oceanic crust forming. Because remember, oceanic crust forms from mafic magma, so it's made of basalts and gabbros. So as these mafic magmas make their way towards the surface, cool and solidify, we start to form oceanic crust. And so what's going to happen now is we have our piece of continental crust. This piece has gone that way, this piece has gone that way, and now in the space between the two, we're going to start forming oceanic crust. So, of course, we've already discussed how oceanic crust is denser than continental crust, how it's also thinner, and so that means our oceanic crust is naturally going to form a topographic low, and of course that topographic low is going to start filling with water, and it's going to produce essentially a very narrow seaway. And then finally, over time, this seaway is going to become wider, and it's going to essentially widen to the point where we now have an ocean basin. So a good example of an ocean basin is, of course, the Atlantic. So running down the middle of the Atlantic, we have the Mid-Atlantic Ridge where new crust is being created. And obviously, if we're thinking about the Atlantic, North America would be over here, and Europe would be over here. And the Mid-Atlantic Ridge and down the middle of the Atlantic Ocean is creating the oceanic crust that's pushing Europe this way and North America that way. Now we have to think about destructive plate boundaries, which are called convergent plate boundaries. This is where we have pieces of crust banging into each other. Now, because we have two different types of crust, it means there's actually going to be three different types of boundaries. We're going to have convergent boundaries where we have oceanic crust meeting oceanic crust. We're going to have convergent boundaries where we have continental crust meeting oceanic crust. And we're going to have convergent boundaries where we have continental crust meeting continental crust. And so these are going to produce different types of boundary with different conditions. So in the case of the ocean-ocean and ocean-continent convergent plate boundaries, we have a situation where we have oceanic crust subducting down into the mantle. So these first two types are going to be associated with subduction. Continental crust, on the other hand, will not subduct. So when we have two pieces of continental crust banging into each other, there can't be subduction. The two pieces of crust will just plow into each other head on. Now, because obviously we have two very large pieces of crust smashing into each other, that means there's going to be lots of tectonic stresses, there's going to be lots of folding, there's going to be lots of faulting, and that means lots and lots of earthquakes. And so convergent plate boundaries are often associated with both shallow and deep earthquakes, and some of them can be extremely large. In fact, most of the time when you see a large earthquake on the news, it's typically occurring at a convergent plate boundary. I should also point out that convergent plate boundaries associated with oceanic crusts, that's the ocean-ocean and the continent-ocean convergent plate boundaries, they are also the locations in which we can form tsunamis. Okay, so let's start with the simplest of the three, the continent-continent convergent plate boundary. Well, in the case of a continent-continent convergent plate boundary, we have two pieces of crust smashing into each other, but both of the pieces of crust are naturally buoyant, so they will not subduct. And so what's going to happen is you're going to have one piece of crust goes headlong into the other piece of crust, and obviously where they smash into each other, you are going to produce, for want of a better way of describing it, a geologic crumple zone. And that, we see that in the form of a mountain range. And the classic example of a continent-continent collision is the Himalayas. So we have India moving north, Asia moving south, and they eventually end up smashing into each other, and that leads to the formation of the Himalayan mountains. In terms of the formation of the Himalayas, the formation started about 50 to 40 million years ago, give or take a bit. So in terms of the mountain range itself, obviously where we have these two pieces of crust smashing into each other, crust gets pushed up to create the topographic high. Obviously, we need to maintain balance, so however much mass you have on the top of the crust, you need to have an equal mass on the bottom. So the crust here thickens up, okay? Because remember, if we have, let's say we have a mountain range that's 2 kilometers high on the surface, well, that means there needs to be 2 kilometers of material at the bottom here to help balance out the weight, otherwise the mountain range would be unstable. So where these two pieces of crust smash into each other, we end up thickening the crust. We obviously end up folding the crust and faulting the crust very badly. So continent-continent convergent plate boundaries are associated with lots of relatively shallow, quite powerful earthquakes. There's no volcanism though. So continent-continent collisions are not associated with volcanoes. And the reason for that is there's not really much melting going on. Obviously, in order to form a volcano, you need magma. If you don't have magma, well, no volcanoes. So continent-continent collisions are not associated with melting, so no magma, so no volcanoes. So the main threat in a continent-continent area is from earthquakes. Okay, so now let's think about oceanic continental convergent plate boundaries. So in this instance, we have cold, dense oceanic crust hitting warm, buoyant continental crust. Now, I've already discussed how the oceanic crust is obviously going to be heavier, and so when these two pieces of crust hit each other, the oceanic crust is naturally going to want to subduct under the continental crust. So we form a subduction zone. Not really a huge shock there. Now, once again, the collision of these two pieces of crust into each other is going to form lots and lots of deformation, or should I say cause lots of deformation. Now, obviously, because the oceanic crust is being subducted, that really doesn't get deformed too badly. A lot of the deformation is accommodated by the continental crust. And so what we'll see is the continental crust folding and faulting, and that will lead to the formation of a mountain range. So a mountain range is mostly the result of sheets of rock being pushed one on top of another. So in the case of a piece of continental crust, so this picture here is going to show the kind of situation we're talking about. So here's our sequence of rocks. We've got this kind of pinkish rock, green rock, and blue rock. Okay, and this sequence of rocks is being squished from the left and from the right. What happens is eventually if you push the rocks too far, they fail. And so what happens is one sheet of rock ends up getting pushed over the top of the other sheet of rock. And because this compression doesn't let up, it happens again and again. So we can see that another layer gets pushed over the top, and then another layer gets pushed over the top. And you can see pretty quickly what's happening is we're going from a sequence of rocks that was this thick, and all of a sudden we're turning it into a sequence of rocks which is this thick. We've formed a topographic high. We've formed our mountain, haven't we? At the same time, we're also folding the rocks. That helps to make layers thicker. And to add even more material to our mountain range, we have lots and lots of intrusions. So big magma chambers get stuck in this mountain range. And we also have volcanoes putting new rocks onto the surface of the mountain range as well. So we have all this material being added to this area which is being actively deformed. And so what ends up happening is we end up forming ourselves a nice big mountain range, of which the classic example is the Andes. So these pictures here are going to kind of show you the kind of things we see when we look at these mountain ranges. So what we'll get is we'll get these sheets of rock being pushed one on top of another. So these black lines here represent the fault planes, so the planes of weakness along which these these layers of rock, these sheets of rock are moving. So you can see that, look where the arrows are going. You can see that this sheet of rock here is being pushed upwards over this sheet of rock. This sheet of rock here is being pushed upwards over the top of this sheet of rock. This sheet of rock here is being pushed upwards over the top of this sheet of rock. So what will happen is we'll end up stacking one sheet of rock on top of another, on top of another, on top of another. What also happens in these areas which are being very strongly deformed is we end up folding the rock. So this is our layer of rock here between these two black lines. And you can see that the layer of rock was initially that thick. But what happens is because we are folding it, we're making the rock go from being this thick to all of a sudden being that thick. So we've managed to increase the thickness of our layer of rock by compressing it. And so once again, this helps to increase the height of our mountain range. So these are the processes that we can, that will be going on the continental crust as it's being actively deformed by the collision. So as pointed out, we have additional mass being added by igneous intrusions. So if I just skip to the next page here, the next slide should I say, what have we got? Well, here's our piece of continental crust and there's our mountain range, which we now know is being produced by deformation. So this area of continental crust here is being actively squished, it's being compressed, and that's causing lots and lots of faulting and lots of folding, which is thickening the crust up, hence the formation of the mountain range. Now the oceanic crust, on the other hand, is coming along. It's subducting down underneath the continental crust. Now, if you remember from the igneous rock portion of the rock lecture, you will know that at a depth of 150 kilometers, the oceanic crust loses water. That water causes the mantle rocks to become unstable and causes them to begin melting. And this will produce a mafic magma. That mafic magma will rise up and it will get stuck at the base of the continental crust. Now, our mafic magma has a temperature of around 950 to 1200 degrees Celsius. It's hot. The continental crust, which is mostly made of granite, will start melting at 650 Celsius if there's water around. And so you're putting something that's nearly double the temperature of nearly twice the temperature of the melting point of the granite. So that means as the mafic magma pools here, it's going to start melting the continental crust. And so by melting the continental crust, what's going to happen is we're going to form a felsic and intermediate magma. So this felsic intermediate magma, that's what's going to rise towards the surface, that's what's going to feed the volcanoes, and that's what's going to produce these large intrusions. Okay, so at these ocean continent convergent plate boundaries, it's not the magma that forms down here that makes it to the surface, it's the magma that forms here. So we have hydration melting here due to the addition of water, but the melting that occurs here is simply thermal melting. We're just heating the crust up to the point where it melts. Okay. Now, obviously, because we have these two pieces of crust moving past each other, lots of friction, so we have lots of earthquakes, we have all this volcanic activity, so there's risk of volcanic eruptions. The earthquakes themselves can be shallow or deep. The deeper earthquakes are caused by the piece of subducting oceanic crust breaking up, or they can also be caused by changes in the mineralogy of the crust. So as this piece of oceanic crust is subducted, temperature and pressure increases, the minerals in it become unstable, and so you get new minerals forming. And so this can actually cause the volume, the thickness of the oceanic crust to change. And some of these changes in volume can actually be quite violent. And so these changes can actually produce these, seismic waves, so these earthquakes, which we can detect. So the ocean continent convergent plate boundaries are actually quite dangerous places to be. We have earthquakes, we have volcanoes, and of course we can also form tsunamis as well. So, not a particularly safe location to live. In terms of ocean-ocean convergent plate boundaries, the situation is very, very similar to the ocean continent convergent plate boundary. However, in this instance, we have oceanic crust meeting oceanic crust. So what happens is one piece of oceanic crust ends up subducting down underneath the other. So the first thing you're thinking to yourself is, well, hold on a minute. If we have two pieces of oceanic crust, well, they're going to have similar physical properties, aren't they? So in theory, they should just come towards each other and they should just bang into each other head on, and we should get the same kind of situation we have at a continent-continent convergent boundary. However, we don't. So the question then becomes is, well, why does one piece of oceanic crust subduct down and the other not? Well, the answer is that most of the time the piece of oceanic crust that does not subduct is attached to a piece of continental crust. And this piece of continental crust which it is attached to gives it extra buoyancy. It's like a life preserver. It helps to give this piece of oceanic crust additional buoyancy so it floats. This piece of oceanic crust, on the other hand, doesn't have this additional buoyancy, so when it hits this piece of oceanic crust, it simply subducts down into the mantle. Now, in the case of a ocean-ocean convergent plate boundary, we do not have a mountain range forming. Instead, what we get is we get a line of islands, and these lines of islands often have a curved shape to them. So they're referred to as island arcs. And what happens is, well, once again, here's our piece of oceanic crust subducting down into the mantle. It makes it to that magic 150 kilometer depth. It dewaters, causes the mantle to melt, producing a mafic magma. That mafic magma rises up and gets stuck at the base of the oceanic crust. So the oceanic crust is made of basalt, and the magma here is also, mafic. So it's same composition. However, the oceanic crust here is cool. The magma is hot, and so what happens is the magma starts to heat up the oceanic crust, and it melts it a little bit. It doesn't melt a lot, just a little bit. And so what happens is we melt a very, very small quantity of the oceanic crust. So we melt the lowest temperature minerals. And in the case of a piece of oceanic crust, the lowest temperature minerals are minerals rich in silicon, aluminum, potassium, sodium. And so what happens is we end up forming a magma that's a mixture between the very calcium, iron, magnesium rich magma that's forming down here and the sodium, potassium, aluminum, silicon rich magma that forms here. The two of them combine together and we end up forming an intermediate magma. So these volcanoes here are going to produce lots and lots of intermediate igneous rocks, so rocks like andesite. And so we see that we see this the resulting melting in the form of these island arcs, these chains of volcanic islands. So here we go. So actually, let's look at the Pacific. So once again, we can see over here we have a few different plate boundaries. Now we can pick out the convergent plate boundaries by the trenches. Okay, because if you remember, the trenches form where the two pieces of crust meet each other. So there's the trench for the ocean continent, and here's the trench for the ocean. And so we can see here are the trenches, and we can actually, if we look here we have the Aleutian Islands, this chain of volcanic islands. So we know we've got one island arc there, and then there's several different island arcs, another one there, there. So many different island arcs. So in these instances here, we have a situation where we have oceanic crust, the Pacific plate, subducting underneath oceanic crust. Now, but this oceanic crust along here is attached to Asia, and therefore Asia gives it added buoyancy. So the result is, of course, these curved chains of volcanoes, which we can, of course, distinguish from the linear chains like the Hawaiian Islands, which we can see here, which are the result of hotspots. So there's no trench, and the chain of volcanoes is a line. It's linear. It's not curved. So our final type of plate boundary are the transform, also sometimes called the conservative plate boundaries. Now they're called conservative because no crust is made or destroyed. So, crust is conserved. So transform plate boundaries are very commonly found within divergent plate boundaries. So we're going back to a picture which we saw earlier. So here are our divergent plate boundaries, one there, and one there. So new crust is being made. But we've already gone and discussed that these ridges here create crust at different rates, and so that means we get this staggered pattern. And obviously these faults here are transform faults. They help to allow these pieces of the ridge to move relative to one another. So these are very large transform faults. Now obviously you have yourself a bit of a conundrum here, because technically this is a divergent plate boundary, but we can see it also has these big transform faults in there. So you can argue, well, are these actual proper transform plate boundaries, or are they just very large transform faults? And I've heard people argue it either way. I personally feel that these big large transform faults are not transform plate boundaries. They're actually part of a divergent plate boundary, so they're not quite right. But either way, the pieces of crust move past each other. In terms of transform plate boundaries, we get no volcanoes because nothing's melting, but we get plenty of strong, shallow earthquakes. So here's a picture of the Atlantic. So we've got Africa over here, so there's Liberia, and South America is going to be off over here to the left. And so we can see our divergent plate boundary coming down here. You can track it quite easily. There it goes. You can see the steps, can't you? Come back here and then down here. So there it is there. Those are our spreading ridges when new crust is being made. And these features here, these are our transform faults. Okay. Now, it's a matter of personal opinion. You can say that these are transform plate boundaries in their own right, or you can say that they're actually part of the larger divergent plate boundary. I personally feel it's the latter, but I would also agree that if you felt it was the former, you would not be incorrect. So these transform faults allow these pieces of crust to move past each other without anything being made or destroyed. So the reason these transform plate boundaries are important is summarized in this image here. So here we have three plates, plate C, plate B, and plate A. So plate A is going to want to move westwards because we're going to form a divergent plate boundary over here, making new crust. And we're going to obviously have to have a convergent plate boundary over here to destroy the old crust. So the plate A is going to move westwards. Now, in order to accommodate that movement, that means that this margin here between A and C and this margin here between A and B must be transform, because otherwise we would not be able to let plate A move as it wanted to. So that's why transform plate boundaries are important. They allow pieces of crust to move past each other without anything being made or destroyed. And of course the classic example of a transform plate boundary is the San Andreas Fault, and you can see it right here. So there's our plate boundary right there. There's a little bit of topography either side. That's because simply the rocks in this area are being squished and damaged by the movement of the pieces of crust, and so that causes a little bit of deformation in this area, hence the topography. So igneous rocks are split into two groups. The first group are the intrusive igneous rocks, also referred to as the plutonic igneous rocks. Now these igneous rocks have coarse to medium crystals, so you can see them with your naked eye. And they are formed when magma cools slowly in the Earth's crust. And because that magma is cooling slowly, it gives the crystals plenty of time to grow, hence the fact they are coarse to medium in size. At the other end of the scale, we have the extrusive or volcanic igneous rocks. Now they have fine crystals, or they're actually a glass. They have no crystals at all, and they're formed by very rapid crystallization at the surface of the Earth. Now the surface of the Earth means both the continent and the seafloor. Now obviously, because this lava is cooling so fast, it doesn't give crystals time to form, in which case you would have a glass. Or if it does give crystals time to form, those crystals don't have time to grow, so they're going to end up being very, very fine. Either way, you cannot see the crystals in an extrusive igneous rock. So straight away, when we look at an igneous rock, we can split it into these two groups instantly, depending on can we see the crystals or can't we see the crystals. Okay, so let's think about magma. So magma is essentially molten rock. In order to make magma, you have to melt a rock. Now magma is also referred to as melt. So every once in a while, if I accidentally say the term melt instead of magma, you know what I mean. Now most magmas are dominated by silicon because most of the major rocks in Earth are dominated by silicate minerals. So when you melt those rocks, you are going to get a silicon dominated magma. So it's going to be a silicate magma, it's called. Now, the vast majority of magmas are generated at depth, and they're due to a number of processes such as deep burial, subduction, or mantle melting, and we're actually going to cover those processes later on. Now, if a magma erupts onto the surface of the Earth, it's called a lava. I'm sure you remember that. And this is the most important one, though. The melt composition and the temperature of that magma controls the types and composition of the minerals that will form from it. Okay, so you can only form the minerals which are stable under the conditions of the magma. So for instance, if you have a stupidly hot magma, let's say 1400 degrees Celsius, you can't start crystallizing low temperature minerals from it. It's just impossible. The temperature's too high, those minerals wouldn't be stable. Also, if your magma is full of magnesium and iron, well, obviously you're going to create minerals which are rich in magnesium and iron. So you're not going to suddenly start creating minerals which are rich in sodium and potassium, because there's just not very much of it in your magma. So the composition of your magma and the temperature of your magma have a very, very major control over the minerals you get, and obviously that's going to affect what type of igneous rock you have. Okay, so if we look at this diagram, there's a lot of stuff going on here. We're going to focus on this top portion right here. So if you remember, igneous rocks are split into 4 groups: felsic, intermediate, mafic, and ultramafic. So these are types of magma: felsic, intermediate, mafic, ultramafic. They're also types of rock. Now, for each of these types of magma, we have a classic volcanic rock and a classic plutonic rock associated with that type of magma. So let's look at the volcanic rocks. If we have a felsic magma and it crystallizes quickly, it forms a rhyolite. Intermediate will give you an andesite, mafic a basalt, and ultramafic a komatiite. If you allow your magmas to cool slowly, so you have a plutonic rock, a felsic magma gives you a granite, intermediate diorite, mafic gabbro, ultramafic peridotite. Now, underneath this, you can see we have this diagram, and it's showing you, the major minerals you would expect to have in your rock. So the question is, what's affecting the minerals you would expect to get? Well, if we come down to the bottom here, we can see we have temperature, which is the pink arrow. So over here at the felsic end of the scale, we have a kind of like minimum magma temperature of around 700 Celsius. Over here at the ultramafic end of the scale, we have a maximum temperature of around 1400 Celsius. So you can see, number one, the types of minerals you get are going to reflect the temperatures. At this end of the scale, you're going to have low temperature minerals. At this end of the scale, you're obviously going to have high temperature minerals. Then we have the change in composition. So as we go from felsic to ultramafic, we have increasing concentrations of iron, magnesium, and calcium. This obviously means at this end of the scale, we're going to have minerals which are rich in iron, magnesium, and calcium. If you go the other way, from ultramafic to felsic, what you have is an increase in sodium and potassium. There's also some other stuff like aluminum as well, actually, come to think of it. And so that means as you go towards this end of the scale, you start seeing more minerals which are rich in sodium, potassium, aluminum, and silicon. So the composition and the temperature is going to affect what you get. So an ultramafic magma, remember, high temperature, lots of iron and magnesium. That means you're going to get a rock dominated by olivine and pyroxene, because those two minerals fit the criteria. Mafic rocks, well, they're quite rich in iron, magnesium, and calcium, so we're going to get a rock that contains lots of pyroxene, quite a lot of calcium-rich plagioclase feldspar, and maybe a little bit of olivine. Intermediate rocks are going to be dominated by plagioclase feldspar. They're going to have muscovite, biotite, and amphibole, and maybe just a little bit of quartz, maybe. And at this end of the scale, we're now at the lowest temperature, largest amount of sodium and potassium. Well, then all of a sudden we start getting low temperature potassium minerals like potassium feldspar appearing. We obviously get quartz, which is a very silicon rich mineral because it's nothing but silicon. We have sodium plagioclase feldspar, there's the sodium. We also have muscovite, biotite, and amphibole appearing. Those are our ferromagnesian phases in this case. So you can see the type of minerals we're getting is a reflection of temperature and composition. And obviously the types of mineral we have essentially allow us to classify the rock that we've got. So if I see I've got my rock and it's absolutely stuffed with olivine, well, it clearly can't be from a felsic magma, can it? The olivine forms at high temperatures with a magma with large amounts of iron and magnesium. So as soon as I see the olivine, I know what type of magma it must have formed from. It's just basic common sense. Okay, so in terms of igneous rock classification, once again, here are four types of magma: felsic, intermediate, mafic and ultramafic. Sometimes if you look in different textbooks, you might actually find the term acid associated with felsic, basic towards mafic and ultrabasic towards ultramafic. These terms here, acid, basic and ultrabasic, are old-fashioned terms. They're not really used anymore. They've been replaced by felsic, mafic and ultramafic. So anyway, so let's just go through the table here. What do we have? Well, we can see that we have the four types of magma, and we can see the temperature ranges associated with each type of magma. We can see the amount of silica, SiO2. We can see that felsic igneous rocks have lots and lots of, felsic igneous magma, have a lot of silica. And so you can create very, very silica-hungry minerals. Things like, potassium feldspar, things like muscovite, biotite, and of course quartz. Quartz is the most silica-hungry mineral because quartz is SiO2, nothing but silica. Now, as we move from felsic to ultramafic, you will notice the amount of silica is steadily decreasing. So that means by the time we're at the ultramafic end of the spectrum, the minerals you're forming, have less silica to work with, so they have to be more silica conservative. And once again, that's another reason you form a mineral like olivine. Olivine doesn't take much silica to make, and so it's a very good mineral for the situation. Now, we also have to think about the volatile content. Now, volatile means gases, and the most common gas in magmas is, of course, water vapor. So when we look at the table here, what can we see? Well, we can see that felsic igneous rocks can in some cases be up to 10% volatiles. Now that's a very, very high upper limit, but nevertheless that is a significant quantity of volatiles, and that's obviously going to affect how the magma behaves. At the other end of the scale, an ultramafic magma has less than 1% volatiles. That's very, very volatile poor. And so that's obviously going to affect how the magma erupted. So if you remember when you were doing earlier courses, you will know that felsic and intermediate magmas are associated with explosive volcanism. And that's because you have these high volatile concentrations. So they are very, very commonly associated with volcanoes that tend to form quite a lot of pyroclastic material due to the explosion, and all the bits of magma getting thrown up into the air creates lots and lots of ash, for instance. In contrast, at the other end of the scale, we have mafic and ultramafic magmas, and obviously when they're erupted onto the surface of the Earth, those eruptions tend to be quite gentle because there's quite a low volatile content. And that means that what you get in these situations is you tend to have volcanic eruptions which are dominated by lava flows. So at this end of the scale, you've got volcanic eruptions which are more dominated by pyroclastics, the part of the eruption caused during the explosive phase. So the types of rocks produced due to the explosive phase of the eruption. However, at this end of the scale, well, there's no explosive phase. So if you don't have the explosive phase, you obviously can't start forming the pyroclastic flows, or pyroclastic material, should I say. And so instead what you have is you have volcanism dominated by lava flows instead. Now, obviously, this is also going to affect the types of minerals that you get. Obviously, you have lots and lots of water in your magma. Well, when you start forming minerals, some of the minerals you form are obviously going to have water in them. At the other end of the scale, an ultramafic magma, very, very water poor, and so the minerals you form will not have water in them because there's just not much water there. In terms of the viscosity of the magma, well, typically the higher the amount of silica, got myself confused there. The higher the amount of silica, the thicker your magma will be. So the lower the amount of silica, the thinner it will be, the more easily it will flow. That's also a reflection of temperature as well. The higher the temperature, the more easily something will flow. The lower the temperature, the more difficult it is for that liquid to flow. And so essentially what we have here is at the ultramafic end, we have a very hot magma with a very low silica content, so it flows very, very easily. At the other end of the scale, we have a very cool magma with a very high silica content, so it flows with difficulty. And when we look at the basic compositions, what do we see? Well, we see at this end of the scale, ultramafic rocks are dominated by magnesium and iron. Mafic rocks contain significant quantities of calcium, magnesium and iron. Intermediate rocks, well, they're intermediate by their nature, so they kind of have this intermediate composition, some silicon, some sodium, some potassium, but also some calcium and some aluminum. And at the felsic end of the scale, we have magmas which are dominated by silicon, sodium and potassium. And so that's obviously going to affect the types of minerals which we get, because obviously the minerals that form will be a reflection of the chemistry and the magma temperature. So we can see how all these things are working together to produce different types of rocks with different types of compositions and different types of minerals. So here we go. So if we look at the common plutonic rocks again, so we have felsic, intermediate, mafic and ultramafic. So we can see here we have ourselves, in all these instances actually, we can see we have the crystals, they're all nice and visible there. So we're definitely dealing with plutonic rocks, otherwise known as intrusive rocks. And we can also see there's a noticeable change in color going from light here to darker over here. Now we can see we're going from kind of a light pink to a kind of 50-50 dark minerals and light minerals here, to a gabbro, which you can see is quite a dark grey. So obviously we have increasing quantities of ferromagnesium minerals. Now once we come to the peridotite here, you'll notice that it's got these beautiful olivine crystals with this lovely apple green colour. So it doesn't actually look that dark when compared to the gabbro, but it is quite a dark rock nevertheless. So the minerals in this case are making it not look quite as dark as it could do. We also have this pyroxenite here, by the way, which is a pyroxene dominated igneous rock. In this case you can see that it's a very, very dark colour there. So anyway, going back through the different types of rocks. So if we have a felsic magma that cools slowly, we get a granite. If we have an intermediate magma that cools slowly, we get ourselves a diorite. If we have a mafic magma that cools slowly, we get a gabbro. And if we have an ultramafic magma that cools slowly, we end up with a peridotite. Okay, now the term peridotite is a bucket term. So peridotite includes several different types of rock. So it includes things like dunites, lertzelites, pyroxenites. They are all put together under the term peridotite, just for simplicity's sake. So in terms of volcanic rocks, also called extrusive rocks, there are actually two different types. We have rocks which are produced by the lava flow itself, and we have rocks which are produced during explosive volcanic eruptions. Now they're referred to as either pyroclastic or volcanoclastic rocks. The two terms are pretty much interchangeable. Now, as we know, once again, our magmas fall into one of four types: felsic, intermediate, mafic and ultramafic. And we know that the compositions of these magmas are different and the temperatures of these magmas are different, so we're going to get different minerals associated with each type of magma. So when we look at something like a komatiite, we know it's going to be dominated by olivine, a bit of pyroxene. Mafic igneous rocks are going to be dominated by lots of pyroxene and lots of calcium plagioclase feldspar. Intermediate igneous rocks, well, they're going to be dominated by a lot of plagioclase feldspar, more sodium rich plagioclase feldspar at this point, but also because there's a little bit of ferromagnesium, well, a little bit of iron and magnesium in the magma as well, you're also going to get some darker minerals present. So you're going to get things like amphibole and biotite appearing. And then at this end of the scale, we have lots of sodium, lots of potassium, lots of aluminum, lots of silicon. So we're going to end up forming quite light coloured minerals. So as we go from felsic to ultramafic, we're going to have a steady darkening of the colour of the rock. So, that's the first way that we classify extrusive igneous rocks. We simply look at the colour of them. So if we look at them here, what do we have? Well, we can see we have the rhyolite here, so that's felsic, the andesite here, intermediate, the basalt here, mafic, and the komatiite here, that's ultramafic. Now, you might have noticed a couple of times that when komatiite appears, it has a little asterisk next to it. And that's simply because komatiites aren't formed anymore. They're not erupted on the surface of the Earth. So the last time we had komatiites really being erupted was all the way back in the Precambrian. And so that means if you want to go and find a fresh komatiite sample, you can't. They're all very, very old, and typically they're all very, very altered. And so the colour of this rock that we have here is not the colour it would have had when it originally formed. So this isn't representative. But nevertheless, what we can see is there is a clear darkening as we go from felsic through intermediate and into mafic. And that's a reflection of the magma composition. So that's the first way we can work out what our extrusive igneous rock might be. In order to get even more information, we have this diagram here. Now, this is the Bowen's reaction series, and it's very similar to the other diagram, but it has a couple of differences to it. Now, obviously, on this side, once again, we have magma temperature, so we have high at this end and low at this end. So if you remember, that's going to be going from about 1,400 degrees Celsius here to around 700 degrees Celsius here. So we have quite a temperature range. You will also see that we have ultramafic, mafic, intermediate and felsic here. So we have our different magma types. Obviously, once again, very, very rich in iron, magnesium and calcium at this end of the scale. Very, very rich in sodium, potassium, aluminum and silicon at this end of the scale. So what do we see? Well, we see ultramafic rocks. Well, we can see they're going to be rich in olivine because we have the arrow there. They're going to have a little bit of pyroxene, and they're going to have some calcium-rich plagioclase feldspar. Now, the nice thing about the Bowen's reaction series is that the amount of the arrow in the field gives you some idea of, what relative proportions to expect in your rock. So if we look at this ultramafic rock, well, we have a huge amount of the olivine arrow in the field. So that means ultramafic rocks are going to naturally be very olivine rich on the whole. There will also be a lesser amount of pyroxene and a lesser amount of calcium-rich plagioclase feldspar. Now, this doesn't always hold true. There are some types of ultramafic rock which are called pyroxenites, and they're dominated by pyroxene. They have a very, very substantial pyroxene component to the rock. So obviously that rule doesn't hold true 100% of the time, but we're talking generally you would expect most ultramafic rocks to have a very, very high olivine content with lesser pyroxene and calcium-rich plagioclase feldspar. For mafic magma, well, what would we expect the mineral composition to be? Well, obviously we can see we expect lots of pyroxene because the pyroxene arrow fills the entire field. Lots of plagioclase feldspar, more at the calcium end of the scale. A little olivine, maybe some amphibole, and maybe a tiny, tiny amount of biotite. Intermediate magmas, well, what would we expect in those? We'd expect lots of plagioclase feldspar, this time more towards the sodium end of the scale. Quite a lot of biotite, quite a lot of amphibole, and maybe under certain rare conditions a little bit of pyroxene sneaking in as well. And then at this end of the scale, at the felsic end, we have potassium feldspar, muscovite and quartz, and maybe a little amphibole, biotite or sodium-rich plagioclase feldspar can sneak in as well. So the amount of each arrow in the field gives you some idea of what the relative proportions are going to be. The Bowen's reaction series obviously also tells you, which ones are the high temperature minerals and which ones are the lower temperature minerals, and so it's showing you the progression of minerals as you go from high temperature over here to low temperature down here. So it's showing you, for instance, the ferromagnesium minerals here, olivine, pyroxene, amphibole and biotite. It's showing you which ones will be stable at the higher temperatures and which ones will be stable at the lower temperatures. So in front of us we have the classic definition of what a mineral should be, or more accurately, the 6 criteria a substance has to meet in order to be considered a mineral. Now these are the classic criteria, so these are the ones that you've probably seen before in earlier courses. So the 6 criteria, of course, naturally occurring, has to be homogeneous, has to be solid at room temperature, so that means 25 degrees Celsius and 1 atmosphere pressure. It has to be inorganic, it has to have a defined chemical formula, and it has to have a crystal lattice. So that means the atoms in it have to be organized in a repeating pattern. So these are the things that a substance has to have to be considered a mineral in the classic sense.